All right, everybody. It's about time to get started here, so let's get organized. Nice to see everybody. Welcome back after Thanksgiving, and welcome to those of you who are somehow not at the NeurIPS conference. It's nice to see you all. So let's see, we've got about 3 more lectures left in this course and a final exam. That's about it. Your homework is due the 5th, so you got some time, but you should get started. And remember that homework includes the midterm. You can and should do make up problems on that midterm exam so that you can, forgive all the sins of your previous mistakes and be ready for the final exam for this course. Before the final, we'll schedule a review session or two, just like the midterm. And by the end of this week, we will try to announce an arrangement for makeup exams. I know a lot of you guys are at SIGGRAPH Asia, one of you is presenting something at Caltech or whatever. We will do our best to accommodate that, but of course, at the end of the day, it's you guys' responsibility to take the final exam for this course. That's what happens when you sign up for a class. So we'll try our best, but you may have to be flexible as well. Any questions, comments, concerns? Yes?
Can I use my late days for the midterm submission?
Sorry, I didn't hear that.
Can I use my late days for the midterm resubmission?
I believe the midterm corrections are just part of your homework, so it would be the same as using your late day for your homework. Yeah. Any other questions? Fabulous. All right, so let's see. So in our previous lecture, we began our discussion of numerical quadrature integration. The basic idea in that class is that we were limited to one dimension, and our goal was to estimate quantities of the form integral from a to b of f of x dx. And the basic idea of that lecture was that there's actually probably a little more flexibility in designing a quadrature rule than you might think at first. In particular, for one thing, the classical quadrature rules that we all remember from our high school calculus class are not necessarily so easy to compare from an accuracy perspective. Remember that, in particular, for example, trapezoid and midpoint integration actually had the same asymptotic amount of error, and in fact, midpoint integration is lower from a constant factor perspective, which is not really what you would expect from a Taylor series kind of perspective, right? The idea that if you add more terms to your Taylor series, like moving from a constant interpolant to a linear interpolant, somehow feels like you should get a better quality integral, but for whatever reason, that's just not what plays out when you write the math down. More generally, we considered quadrature rules that basically approximated this integral here with a quantity of the form sum wi f of xi. So for example, for midpoint rule, all the w's are the same and the x's are evenly spaced. And then toward the end of the lecture, we basically discovered this kind of fun thing that if we allow not only the w's to be variables when we're trying to work out a quadrature rule, but also the x's, we can strategically choose both at the same time to choose quadrature rules that are really high order accurate, at least for example, for polynomials. Right, so that was the idea of this Gauss quadrature rule, which basically said, okay, what we're going to do is solve a big system of equations that sets this thing equal to the proper integral for some fixed set of functions. And if there's n terms of the sum, then you have sort of two options, either a linear system to solve if you fix the x's and just solve for the w's, or some really nasty nonlinear thing if you allow both the x's and the w's to move around at the same time. So that was the basic idea of the previous lecture. Today we're going to conclude our discussion of integration by really quickly mentioning some strategies for multivariable integration. Sadly, this is largely a topic that we'll have to kind of defer for another class. If you take, for example, a course on probability, you'll spend a lot of time basically working on multivariate integration, although it tends to come in slightly different language. And unfortunately for us, this class, because we don't have probability as a prerequisite, it's a little bit tricky to dig into the details of that. But it is worth mentioning briefly some of the basic strategies for people to use in multivariate integration, and to mention that, of course, not all of the quadrature rules out there are stochastic. There are plenty of ones that are deterministic, and basically extensions of what we've already done. So as the simplest example, let's say that I want to integrate a function on some rectangle R, which is like the interval from 0 to 1, copied a bunch of times. Then there's, of course, a very... It's funny because I think in a lot of our minds, we would think of this as a definition, but it's actually a theorem, saying that if I want to integrate over R some function f of x dx, and here to be clear, x is a vector, then we can do this thing that sometimes I think is cute. People call like disintegration, um, which is basically the rectangle. It's particularly simple. We can do sort of this integrated formula like this. I guess dx like that. And I think a thing that's a little bit subtle, but it actually kind of matters from perspective of numerical methods, is that these are not the same expression. I mean, of course, in math you prove that they're equal to one another, but the definitions of these two integrals are slightly different. This is an integral just in a multidimensional region. This is a bunch of one-dimensional integrals, right? Like, so if I kind of separated out this piece, for example, this is now a function of the outer x that's giving the integral over the rest of the slices of the rectangle. So for example, like vertical slices or something like that. Does that make sense, why these things are slightly different? Now, notice on the right-hand side, of course, we can now take any of our one-dimensional integration functions and apply it to a multidimensional integration by just kind of doing this recursively. So as a simple example, let's say that I want to integrate on a square. So I have 0, 1, 0, 1, f of xy d y dx, right? Then, of course, basically by this formula here, well, I guess disintegrated here. This is the same as the integral of 0, 1 g of x dx, where g of x we define as the integral of f xy from 0 to 1 dy. So here it's like made a little bit more obvious that this is a bunch of one-dimensional integrals. Does this little breakdown make sense? This is one of these things that I think like I'm writing a lot, but actually is really quite obvious. And so a very simple kind of recursive thing that I could do to approximate this integral on the square is to use any of the quadrature techniques that we derived in our last lecture to first approximate the function g at a bunch of different points x, and then apply that same quadrature rule on the outside to do the integral over the rectangle. And this will work. It's perfectly fine. It has the same approximation quality as the sort of outer formula. Can anybody guess what goes wrong with this in about dimension bigger than like 2-ish? Yeah, on. That's exactly right. So like basically, if you think about it, what we're doing is we're taking our domain and we're just, in this case, just a rectangle, and we're sticking a giant grid over it, right? And in particular, notice what happens. So the theory from our previous lecture says to get a particular amount of quality, what do we have to do? For any one of these, a single dimension, we need to control that delta x, right? And that basically, of course, delta x is inversely proportional to the number of samples that you need along that one-dimensional line to make an integral, right? So if I want to make order delta x error in both vertical and horizontal, now I need to make an n by n grid, which is, of course, quadratic in the size of my problem, whereas everything we did in our previous lecture is linear. Or if we do cubic things, then now it's cubic in the size of our problem, and so on. And so the basic issue with using the classical quadrature rule in high dimension is that it exponentiates in terms of complexity. And so basically the sort of high-level takeaway of a lot of numerical techniques out there, sadly, again, I'm going to defer, or if you want to read about this stuff, email me, because I need a proofreader for the randomized algorithm part of the textbook, which we will not cover in this class. Basically does one of two things. On the one hand, by the way, one thing that we'd have to worry about in high dimension is, of course, a lot of our regions are not just rectangles, they're like some blobs. That's not a big deal, but of course now you have to deal with like intersecting a blob with a grid, which is a little bit annoying. So for example, here we need to exclude that region. But typically what happens is a dimension bigger than about 2-ish, there's an algorithm that feels stupid but actually turns out to be more efficient in expectation. Oh no, I gave it away. Which is as follows. A formula that I think you guys have all, I mean, if you unroll the prerequisites in this class, I think you've all seen a random variable at least one point in your life. So very quickly, one link between calculus and probability, in some sense, or in another sense, it's just a definition, says the following. Let's say that I compute the following quantity. So I have some region in Rn, which is omega, and I integrate a function f of x. Here x is a vector, over that region. By the way, in this course, we'll assume f is like c infinity or whatever you need to make integrals make sense. We're not going to worry about like Lebesgue versus whatever. What is this quantity? Well, here the notation on the left-hand side is like the area of omega. So we're taking the integral of omega divided by the area. There's a different notation for this in probability. It really is just notation, by the way, which is that this is the expectation, I guess, of a random variable drawn from the uniform distribution omega of f of x, right? And basically, this link, which, by the way, I should have like not erased the boards from Philippe Rigolet's class right before this one, because this is exactly what he's teaching, says that you can obtain this integral in one of two ways. One is to do basically the kind of stuff we've talked about in the last couple lectures. Another one, at least up to a factor of the area of the domain, that's actually kind of a tricky point, you can obtain by throwing darts, right? So what I do is I randomly draw points x in the region omega, which, by the way, might not be so obvious if omega is some weird shape, but that's a different problem. And then I just compute the value, I evaluate the value of f of x, and then I just average for a bunch of samples, right? And the more samples that I draw, right, the closer that I get to this integral. So again, I throw darts in the region. I see your hand, Jonah. I evaluate the value f of x, and then I average. So in other words, like maybe this is like 1 over n with a sum over I, 1 to n of f xi, where xi is drawn from the omega. Does that make sense? Jonah? Oh, sure. This is called an expectation. This is basically just fancy probability language for average value. Yeah. In fact, it's kind of, in my mind, it's defined by the expression on the left. Depending what textbook you start with, you may or may not do that. Yeah. Don't worry about it. Like, this class obviously is not a randomized algorithms class. We're not going to hold you too accountable to this stuff. Now, I think a really interesting question you could ask is the following. I guess actually I was using capital N before. Oh, capital N I guess was my dimension. So yeah, sure, little n's fine. When we talk about randomized algorithms, suddenly there's a big trade-off between lots of things we haven't had to think about in this course, right? If I throw a new set of darts, then I'll get a different value of the integral. So it's not one of the cases where every time I run my algorithm, I get the same thing, right? In fact, this particular formula we would call unbiased, meaning if I run this algorithm a bunch of times and I average the result, it will give me the true integral that I want. There are other estimators out there that are biased but converge more quickly, or all kinds of stuff. There's a huge literature on this stuff. I love it. I can talk about it for days. Right, so the question is, how do you evaluate numerical algorithms like this? And you can still ask questions about convergence and complexity. It's just that you have to now think about it in a slightly different way, which is that it kind of looks like the variance of this estimator. Do you see that like this average is itself a random variable? Like if I define a randomized algorithm, which is draw 10 points and average the value of 10 things, then probably something that we can observe is that as I increase n, or I think in the textbook it's k, sorry, we expect the variance of that random variable to go to 0, right? In other words, if I run the algorithm a bunch of times, it should be a better and better estimator of the integral that I'm trying to compute. Again, up to this factor of area, but it turns out you can also do this by a similar strategy. For example, you could draw a big box around omega, throw darts, and then just count how many are actually inside of omega. Subtle point there is that this is going to be biased estimator if you then divide by that area. But that's a thing to think about for later. But in any event, if we do this estimator, I think a reasonable question is how many samples do I need to get a good integral? And like, how does it compare, for example, to these gridded strategies that we see on the previous board here? And here's kind of an interesting thing, which is that the convergence rate of these stochastic estimators kind of converges like 1 over the square root of n. Right? So if you think about the error of this thing, roughly, where error has to be defined a little bit carefully in this domain, then essentially error decreases sublinearly. Do you see this? So this feels like a really crappy estimator of an integral. Like there's typically like the things that we've done in this course look closer to like 1 over n squared, right? Because remember that delta x and n are kind of inversely proportional to each other. However, this thing, despite my choice of the letter n here, has a really weird and interesting property, which I think is really the toehold into basically an entire course on MCMC and randomized estimation and so on, which is that there's no dimension dependence. So this estimator converges like 1 over the square root of n in 1 dimension. It also converges like 1 over the square root of n in 1,000 dimensions. Whereas what happens with our strategy up here with this integration is, if you think about it, the number of samples n that you need exponentiates in the dimension. And so basically there's kind of an interesting thing, which is even the world's worst randomized estimator in dimension bigger than like about 3-ish begins to dominate over the gridded strategy if you talk about apples to apples and like comparing error. Now, of course, there's a lot of other issues with using these kinds of things. They're randomized, they can be unreliable. For example, like let's say that I were integrating a function and it just has like a little blip right there, then like throwing darts would be a really bad strategy because like all the interesting part of the integral is like hiding in this little tiny part of my function. And so, of course, if you take a more advanced course on these things, you talk about all kinds of algorithms that try to kind of say, well, I shouldn't like, okay, your instructor, when he plays darts at a bar, probably does something very similar to this, but most of you guys do not throw darts with your eyes closed. You actually look at your function and you throw and you try to like have a feedback loop. And that basically leads you to a class of algorithms called Markov chain Monte Carlo, which is basically trying to suggest that if I can take these samples xi and start to kind of shift them and bias them based on learning about the shape of my function f, then maybe I can get an estimator that converges even more quickly. So in any event, this is mostly just like a little bit of a toehold into the literature in this domain. I'll let you guys read about this at home. But essentially all this is to say that the quadrature rules we've talked about today are perfectly valid in higher dimension, and certainly in 1 dimension, they look like 1 over n, and we have 1 over square root of n, so they win. However, as the dimension increases, that advantage very quickly goes away. And at that point, it becomes a lot less clear that the strategies we've talked about so far are really the right thing to do relative to just throwing darts. So in any event, someday when the department allows me to teach a 2-semester-long numerical methods course, we can really focus on that and do all kinds of interesting things. In fact, once your software is allowed to flip a coin, that sort of unlocks an entirely new class of algorithms. We've briefly mentioned stochastic gradient descent in this class as one example, but there's so many others. So for example, if I have a gigantic matrix and I want to approximate its SVD, and I only care about its top 5 eigenvectors or something like that, you might ask whether there's some randomized algorithm that can like use a 5x5 SVD instead of a billion by billion SVD to capture that pretty accurately in a randomized fashion. And the answer is yes. There's all kinds of really neat algorithms out there in this domain. But that's all we get today. So in any event, if you like this kind of thing, these are called Monte Carlo estimators. Markov chain Monte Carlo is specifically when the x's kind of depend on one another in a random walk. And it's a really beautiful area of math, one that people devote their entire careers to studying. So sadly, we can't do that in 15 minutes in lecture. Yes?
To estimate the integral correctly, we will also need to know the volume or the area or whatever.
That's exactly right. So in order to compute this integral, we also need the volume. Here's a very simple way to do it, but it's also problematic, which is, for instance, let's say that I do know that the omega is bounded. So at the very least, I have some big rectangle that sits underneath it. Then notice that, well, I can just write it here, that the integral over omega is equal to the integral over that rectangle that bounds it of just like the indicator function of x is in omega dx, right? So I could just like throw a bunch of darts. Let's say this is in the unit rectangle, if I'm lucky, of course, otherwise I'll have to do some scaling. So maybe this thing is 0, 1 to the n. What can I do? Well, I can basically figure out the fraction of the unit box, which contains omega, and that gives me an estimator of this thing. If you're worried about your numerical algorithms, you should be, because of course this is not the quantity that we really want. What we really want is this to the -1. And it turns out that the second that you take a random variable and you do anything nonlinear to it, if you estimate it stochastically like this, you start throwing darts, then this thing is what we call biased, meaning that if I compute this estimator with a finite set of samples and I repeat it a few times and take the average of the result, it will not average out to the area of omega, or 1 over the area, rather. If you're curious, the place to look for this kind of thing, just to see a little piece of theory that tells you a little more about this, is Jensen inequality, which basically gives you a bound for this value from finite samples versus taking sort of the proper thing. Yes? Can you get an unbiased estimator for 1 over area? I believe the answer is yes, but it's tricky. So it turns out for non-polynomial functions, what's the theorem here? You can't do it with a finite set of random variables, I think is the way this goes. You shouldn't quote me on this, I'm not a probabilist, but I believe, so like for instance, if I want, now I'm going to get carried away. This is not the topic of this course at all, just to be clear. Like if I want, for example, the expectation over x drawn from some p of x squared, like that, this is a polynomial function, so it turns out there's some things that we can do. But the second that it's non-polynomial, then like essentially what you have to do is, for example, there's this like Taylor series for 1 over 1 minus x, which is I think 1 plus x squared plus like that. So what you can do, which is super clever, is related to these Russian roulette estimators. You kind of randomly draw from a probability distribution over the positive integers a number of terms that you're going to compute in this series. And then for each of these terms, you use an unbiased estimator of the polynomial thing. And if you construct it just right, you can get the whole thing to be unbiased, but super high variance. Anyway, there's like probability is just this giant bag of tricks, and I hate it. Okay, so with that, we're going to mention one last little thing about numerical quadrature. Of course, in this class, we keep doing the same cycle. We talk about a problem, we talk about its applications, we talk about some algorithms, and finally, we need to talk about conditioning. And in particular, in quadrature, one thing that we might ask is essentially, in some sense, evaluating the stability of a quadrature rule. So remember, we have quadrature rules of this form. By the way, the high dimension quadrature rules also take this form. They're just vectorial exercise. And now we could ask a slightly different question that we've asked before. So far what we've asked are questions where we have the quadrature rule on f, and we start to subtract off the true integral. A different question we could ask is, we have the quadrature rule on f, and then we have a quadrature rule on f, but accidentally our samples were a little wrong. How far off does our integral become? Do you guys see how these are two different questions? One of them is accuracy, and the other one is stability. So for stability, it turns out that it's pretty easy to derive a bound. In fact, there's a whole category of bounds using like Holder inequality, but we'll do the simple one. Something like this. So we're trying to ask whether our quadrature rule is stable or not. And here, what we're going to do is we'll say our quadrature rule Q of f is equal to the sum Wi f xi. And just for ease of notation, the argument carries through in high dimension. We'll assume we're in 1D, so all of our xi's are in some interval from a to b. Okay? And now let's see if we can bound the quantity on the screen. Namely, what we're going to do is perturb f to some function f hat. So in other words, like, I wanted the integral of a function f, but I drew my samples. They were all a little bit wrong. There's numerical error, whatever. I got f hat. Notice that those are different things. Like, it could be in a world of precise, perfect arithmetic. I have an awesome quadrature rule, but it's super unstable. Like, if I get f a little wrong, then it blows up. I think the likelihood of that happening is pretty low, because if it's a good quadrature rule, it should probably also work well for f hat. But you can imagine a universe where that happens. So we'll evaluate stability in the norm that makes this calculation easiest, which in this case is the L infinity norm, which you guys might recall is equal to the max, or really the sup of x in a to b of the absolute value of f of x minus f hat. Okay. So in other words, what are we asking? We're saying if f and f hat, that's an equal sign, are like not that far apart from one point to the next, can we make sure that our estimation of the integral also doesn't change that much? That makes sense? Okay, so let's compute this bound really quick. This is an easy one. So we have the quadrature rule applied to f minus the quadrature rule applied to f hat divided by the norm of f minus f hat. So this is our notion of stability. And one thing that we can do is just not think too hard. We have a quadrature rule right there, so let's just plug it in. And what are we going to get? We will get that this is the sum over Wi of f of xi minus f hat of xi, like that, divided by the L infinity norm someday. when I remember to revise my lectures, I'm going to not carry around this fraction because it's just an annoyance. Okay. Everybody with me so far? So, in this class, we basically only have one strategy for deriving these kinds of inequalities. Namely, we have the absolute value of a sum. So we can upper bound that by the sum of the absolute values. This is the triangle inequality, right? So in particular, what is this thing going to be? It is less than or equal to the sum over I of the absolute value of wi, f of xi minus f hat of xi, like that, divided by f minus f hat. Does this expression make sense? All right. So now we're cooking with gas. Does anybody see how we're going to finish our proof here? Let's take a look at this quantity here. Right. This is the difference between values of f at some sensible points at xi. What do we know?
Yeah, like by construction, it's less than the denominator.
Yeah, this thing is less. If we don't even think that much, every single one of these things is less than or equal to f minus f hat L infinity. Does that make sense? Because just by definition, this is the max of this quantity, right? So if I plug in that inequality, the numerator and the denominator cancel. And we get that this is less than or equal to the sum of the absolute value of wi. Or a different way to write that, if we think of w as a vector, is that this is the L1 norm. Notice a kind of funny thing happened, which is that our notion of error for f was in L infinity, and then the error we got for w was in L1. That's not a mistake. These are pairs of, what's the word? So not conjugate in this case. If you're curious, the theorem, I think, is the Holder inequality, which is the more general version of this statement. But let's step back and see what this says. So essentially, we have this push-pull between two different aspects of quadrature rules, right? One of them is just how well it does as a function of delta x, or as a function of the number of samples we have. Another one is just if I get f a little bit wrong, like how far off am I going to be? And those don't have to be the same thing, right? And so in particular, I think what we proved is a pretty reasonable statement, which says the following. Essentially, we can upper bound the stability of our calculation of an integral, like the relative error, based on the L1 norm of the set of coefficients that we have, right? So in other words, think about what this is saying. Like, so suppose that I've got some function and I want to compute its integral. We put our xi's wherever we're going to do it, and that each of these xi's, I also need to put some weighting, right? Like, for example, the height of the rectangle at that point, or whatever. I'm drawing this very poorly, right? If those weights are themselves really, really big and really small, then of course, what does that mean? That's going to amplify the error that we see in the values of f, and then our integral is going to be inaccurate, right? And so, like, for example, remember the Simpson's rule for quadrature was relatively accurate, right? This was, I think, like fourth order, third order accurate. But whereas the midpoint integration rule had a bunch of ones, the Simpson rule had like a 1, 2, 1, 2 kind of pattern to it. And so essentially, what is this saying? It's saying it's maybe more accurate as the x's are more sampled more densely. However, that quadrature rule is less likely to be stable if our function is evaluated incorrectly. Make sense? Just like one final footnote for numerical integration. Good news is I think this is way easier than most of the stuff we've done in this class. Excellent. In that case, we just talked about numerical integrals, so you can probably guess what's coming next in this course, which is now we need to do the other half of calculus and talk about numerical derivatives. Numerical derivatives are kind of funny. I love numerical differentiation. I can talk about this stuff for days. I think it's so much fun. This is probably true for most topics in this class. Numerical differentiation is a little bit of an outlier in this course. I mean, so far, when we've talked about algorithms for numerical methods, certainly everything we've done post matrix inversion, all of our algorithms basically have the following property, which is if I run it longer, I can get a more accurate answer. Numerical differentiation, that's like not really a problem. In particular, like let's say that I have a one-dimensional function, f of x, and I want to compute its derivative. Remember that derivatives are limits, so like a computer can't do a limit because that's like some kind of infinity thing, at least without a symbolic computation system. So instead, I have some expression like this, minus f of x divided by h, and maybe I just take some positive h, and I say, okay, I'm just going to approximate it with that for some h bigger than 0. Okay? Like, I think all of you guys, if I gave you a function f of x of some variable, I asked you to approximate the derivative on the computer, you'd type this expression in and you'd give me the result. You'd probably choose h to be 10 to the minus 8 and be done with it, right? Now, I think this is one of these really subtle areas. In some sense, this expression on the left-hand side suggests that I should do the following thing, which take h to be just like the smallest possible number, like numerical epsilon, like whatever, like world's tiniest h, and then the approximation on the left-hand side is going to get as good as possible from a mathematical perspective, right? And indeed, that's absolutely the case. So in particular, if I run that experiment, I could do the following thing. Let's actually define this object. By the way, this is called a divided difference. Let's give it a name. Let's call it d, which is a function of that spacing h. And notice that it's a function. It has the property that the limit as h goes to 0 is f prime of x. Does that make sense? Now, here's what math tells me, which is the following. Let's make a little plot. I'm going to simulate MATLAB for you guys. So here's h, and here is the difference between d of h and f prime of x. So clearly, assuming the limit exists, the value at 0 should be what? Or like the value very, very close to 0, I suppose. Should be 0, right? This is the error of the divided difference of this limit. So the error should start like this. And then mathematically, as h gets bigger, it probably kind of grows. Right? And so that's what we might predict when we write software. We code this formula. Leticia, you're looking concerned. What did I do wrong? Oh, no problem. So let me have you get unlocked. So d of h is this expression as a function of h. So as h goes to 0, this approaches f prime, right? So this is the alpha value of the difference between d and f prime, so like the error in my approximation. And so mathematically, what I would predict is as h goes to 0, the error goes to 0. And as h grows, the error gets worse. Okay. Does anybody want to guess what happens in practice? Yeah, one of you two. Yeah, so in reality, I make a plot like this. So this is math. Here's reality. Where reality and MATLAB are the same thing, as we all know. We form this plot, and in fact, what you'll find is that it looks like that. Let's think about why. Now, again, this has nothing to do with computational complexity. I think that's what sort of distinguishes this topic from other parts of this course, right? Because this formula is equally easy to type in for any age, right? But the issue here is approximation quality. So in some sense, we can take this plot and we can divide it into two regimes here. On the right-hand side, indeed, this is sort of approximation error, just like on the left plot. So basically, if h is too big, then this divided difference is no longer a good proxy for f prime. Does that make sense? But what happens when h is too small? Think back to like lecture 1 of this course. Yeah, we have catastrophic cancellation, and we're dividing by a tiny number, right? So basically, if h is really itty-bitty, it could easily be the case that this difference basically just is like 0 or very close to 0. You have a very small amount of precision. So suddenly the numerical error totally blows up for this expression. So that's the really subtle point of numerical differentiation. It's not an efficiency consideration. It's all about accuracy. By the way, in general, this plot doesn't look so smooth. It looks like that because, you know, like the bits start to come into play and numbers are unevenly spaced and so on. And so that's the basic issue, is that if h is too small, you run into stability problems, not efficiency problems. There's a slight different matter, which is thinking about Jacobians versus functions on the real numbers. Like if I have a function on multiple variables, can I do more clever derivative approximation? Let's punt on that for now. There are clever things to do, especially on the complex numbers. There's some really cool tricks. Our postdoc in our lab, Ahmed, is like really into one of them that I've never heard of before. But for now, we'll just talk about 1D. And then, of course, you could use the 1D things to do Jacobians by just iterating element by element, which incidentally, I think is roughly what 98% of the numerical world does. Okay, so let's talk about different strategies for numerical differentiation. There are actually many out there, which is kind of surprising because it feels like you would just plug into this formula here. They vary in complexity, accuracy, all the rest. Kind of following our previous lecture, of course, one thing that we could do is take our function f of x, write it in a basis by applying our interpolation lecture, and then approximating the derivative as the derivative of the sum of the basis functions. That's perfectly fine. But it is worth noting that oftentimes this derivative function has like weirder properties than the function itself. By the way, if you're a signal processing person, should be unsurprising because, as you probably know, differentiation amplifies high frequencies if you're into the Fourier transform. So let's think of an example of that. So remember that one of the strategies we had for interpolation, like let's say I have a function, I have it sampled at a bunch of points, like that, might be to just connect them with straight lines. This leads to what we call a piecewise linear interpolant, right? So notice when we integrate, somehow we're like summarizing this interpolation function over an interval, which feels like it's sort of stabilizing thing. We're like taking an average. But of course, derivatives are doing the opposite of that. In fact, if I pass, so this is the, I don't know, f, if I have f prime, what's that going to look like? What's the derivative of a line? Alicia, a little louder. The slope, that's right, it's a constant. So here, okay, I noticed when I taught this class last time, I didn't account for the fact that when things slope down, they're negative. There. That's what the derivative of this thing looks like. So in particular, if f is piecewise linear, notice that its derivative is not. And so this can lead to some problems. In particular, like if we're solving a differential equation with these kinds of approximation, we have to be quite careful because we need our interpolants to be at least as high order as the differential equation we're trying to solve. Sadly, in this class, we're not probably going to get to partial differential equation, but just to give you guys a little bit of a hint, there's some really cool and interesting problems that you can do here by kind of combining integrals and derivatives in clever ways. So to give you just like a tiptoe into that universe, let's say that I wanted to solve an equation that looks kind of like, f double prime of x equals g of x. So I'm like given g and I'm trying to find f. Because this is technically a quadrature problem in 1D. But I could also imagine doing this by like measuring the error of this expression and trying to make it small or something like that. So somehow it feels like I need to choose an interpolant with at least two derivatives to solve this problem, right? Because otherwise f double prime doesn't make any sense. So like that piecewise linear thing, if I took derivatives, two derivatives of it, I'd just get 0, right? So that wouldn't be a very exciting interpolant. Just to give you a little toehold into what people do in differential equations, since this class we won't probably get to it, here's a really fun thing. Oftentimes you don't actually need the derivative of a function. What you need is something a little bit weaker than that, which is to say, let's say that I take any other function, psi. I could say, well, then for any psi, the integral of f double prime times psi should equal the integral of g times psi. Certainly this direction is pretty clear. It's actually an if and only if for a broad class of functions like that. And so a very typical way to solve differential equation is to say, actually, the thing that I really care about is kind of interesting. It's kind of like, rather than like doing your measurements directly, it's like, like walks like a duck, acts like a duck. That must be the solution to your differential equation. In particular, let's say that I solve this on some interval a to b. Anybody have a guess what I'm going to do here? There's a rule from high school calculus. Anytime you see the product of two things and one of them's differentiated, should be screaming out to you. Yes, on. Integration by parts. That's right, my favorite rule. So in particular, notice that this is like psi prime times f prime from a to b minus the integral from a to b of, did I do this right? No, I didn't. It should be psi times f minus f prime psi prime ds. Right, this is integration by parts up to your instructor getting confused. So here's a really beautiful thing. I can solve this second order problem by setting these two things equal to each other. And notice that that only ever needs one derivative. And so in fact, it turns out a lot of algorithms, this is just to give you a little Google search term because I think it's cool. This is called the weak form of a differential equation. And this is sort of actually the toehold into most numerical methods that solve things where you didn't actually need the derivative, you're trying to solve a problem in terms of the derivative, then oftentimes you can integrate it out, and what you need is an interpolant that's maybe half as crazy as what you thought. This is all just a byproduct of integration by parts. By the way, the higher dimensional version of integration by parts, remember what that's called? It's everybody's least favorite thing from college calculus class. Stokes theorem, right? Or like Stokes theorem, divergence theorem, Green's theorem. What are some of the other ones? They're all basically the same. They're all just integration by parts. I feel like they make a way bigger deal out of it than they should in calculus class. Okay, so in any event, this is the kind of strategy that gets used in these sorts of calculations. Like I might write my functions on a basis, set them equal to each other, do all these kinds of tricks. But of course, a lot of numerical differentiation algorithms just work directly with these expressions rather than going through all the bother of interpolation and then differentiating through the interpolant. So it's worth talking about these formulas as well. In particular, we could go back to our definition of the derivative like this. And basically, we could say, okay, this is a limit, but if I choose any finite and positive h, then I get a perfectly reasonable approximation. And we could ask a very good question, I think, which is what is the actual approximation quality of this approximation? So in other words, if I choose a positive h, how good do I think this estimation is going to be of the actual derivative? Lucky for us, the argument is quite straightforward. It's just using Taylor series, which is unsurprising. I'm rushing because I want to get to Richardson extrapolation, which I think is cool. Okay, so it's actually a very straightforward argument. F of x plus h is just f of x plus h f prime of x plus, let's do one more term of this thing. 1/2 h squared f double prime of x plus order h cubed, like that. Okay. So notice that we can immediately read off of this expression by just kind of rearranging it, right? So I can subtract f of x from both sides and divide by h. And what am I going to get? I will get that f x plus h minus f of x divided by h is equal to f prime of x, to be the tiniest bit careful, plus 1/2 h f double prime of x plus, and of course this is big O of h, right? So what do we expect? If we made that plot of our error, like we had, and then I covered up on the board, we would expect that error to kind of look linear as for small h. That makes sense? Okay. Now, one thing we could do is just for fun and profit, see if we can derive some other estimators of this thing and see if they have better properties. There's one really dumb estimator, which is if we also do fx minus h, kind of applying similar symmetry arguments to what we had in our previous lecture on quadrature, then of course this is f of x minus h f prime of x plus 1/2 h squared. I promise there's a reason why I'm writing these extra terms. Double prime of x plus order h cubed, like that. Notice that this already leads to a second approximation of the derivative, which I'm not even going to bother writing on the board, which is the backward difference, which unsurprisingly has the same order of accuracy. Everybody agree with me? Okay, good. Now here's a kind of fun thing that you can do. Let's take this expression and subtract that one and divide by 2h. Right? So in other words, I've done derivative by pointing to the right. I can do derivative by pointing to the left. Now I'm going to do derivative over the whole interval. Right? So in particular, if I put these two things together, I have f of x plus h minus f of x minus h. Notice that the width of my interval is now 2h, so I probably want to divide by 2h, like that. Can we do this together, friends? Okay, so first of all, we subtract that from that, and we get 0. Great. We subtract this guy from that, we get 2h f prime divided by 2h, so this is f prime of x. And oh my god, look at what happened. The quadratic terms are actually the same, so when we subtract them, we get 0. And what we're left with is order h, squared, because we divided by h. Okay? Now, what does that mean? For one thing, basically we've shown that we can get a better approximation of f prime by plugging into this formula on the screen here. This kind of feels spiritually right. I mean, if you do something kind of symmetric, it feels better. Does this matter in reality? I mean, again, none of these algorithms, I mean, they all take the same computation time. I could just put in a smaller h. You're all nodding, but you should be saying, no, Justin, you just told us. You drew all these plots on the board. Don't be stupid. These are clearly different algorithms. Can somebody explain what's going on here? Yeah.
Because you can't do arbitrarily small h without running into numerical.
That's exactly right. So let's think about it this way. We have some numerical problem. And what have we shown? We've shown that basically, remember that this is for h being small. So h squared is a good thing. That means it converges more quickly. Yeah? So here's like kind of a schematic of what's going on. So here's, I'm going to make this up as we go along. Here our horizontal axis is h. And here we've got the error of the linear, the forward difference. And here we have error of what we call central difference, like that, right? And like, basically what we've shown that for a larger h, right, the central difference is still going to give us an okay error, right? So maybe like if I have some fixed amount of tolerable error in my derivative computation, then like this is going to be like the okay point for central difference, and like this is going to be the okay point for forward difference. Does that make sense? So I have like a more wiggle room with h to do this kind of thing. Now in the numerator and the denominator, like the catastrophic cancellation is very similar for these two expressions. So roughly, here's what happens. Here is where cancellation starts happening. Right, because you're dividing by either h or 2h, so like at most they're a factor of 2, but this is like asymptotically better, right? So now hopefully this little schematic starts to help you guys understand why actually, and like the reality is, this makes a big difference when you write your code. Like this is like one of these things that feels like just a detail but actually really matters. Essentially the crossover point where, suddenly numerical error starts to kick in is oftentimes happens before the just approximation error forward difference is okay. Let me try that sentence again. There's some region where forward difference approximation is okay, right? That region oftentimes is contained within the region where numerical error becomes a problem, right? In other words, the h that I would need for forward difference approximation to work is too small before my calculation is just unreliable because of rounding, right? So basically by using central difference, I've widened that interval, right? I've widened the interval where my approximation from a divided difference perspective is okay. And now the crossover point where like numerical error doesn't become such a big issue, like catastrophic cancellation doesn't kick in, that stays in roughly the same point, but now I have more space to choose an h that gives me an accurate approximation, right? So that's why these things matter. In fact, actually, I've noticed this, I've now noticed this with multiple years of graduate students in my office that are debugging their code. In particular, a very popular thing to do right now in like software like PyTorch is to define what people call a custom backward function. You guys, I don't know if you've encountered this before. At the end of the lecture, if we have time, we'll talk about backpropagation. But essentially, the basic idea here is that like algorithms like PyTorch or software like PyTorch, its job in life is to give you a closed form derivative. This is not an approximation. It tries to actually give you the true derivative of some function. And it has the option for you to code your own derivative formula. So like maybe like PyTorch doesn't have cosine in it, so I need to add like a special cosine function, right? And then I need to also tell PyTorch what the derivative of my forward pass is, right? So like derivative of cosine is minus sine. Now, those things get nasty. I mean, cosine and sine is easy enough, but like oftentimes those are really, really yucky. So for example, my PhD student right now is working through differentiating through the inverse of a matrix, and that's a yucky expression. In that case, a very typical thing to do is to code your PyTorch code and then to use expressions like this to just debug it, right? Like, so in other words, I have this software that should give me the true derivative of my function. I then just compute it numerically and I make sure those things agree. Here's a very typical thing. This is, by the way, all numerical software includes this functionality. It's usually called derivative check. It's certainly in Python and SciPy and MATLAB and so on, where it'll just do this for you. It'll just iterate over the elements of a Jacobian, evaluate this expression, and see if they agree. Oftentimes, that code will just yell at you if you use the default setting, which is because it'll use forward difference, and it turns out your derivative is perfectly fine, but actually what's wrong is the derivative checker tool isn't accurate enough. And then when you swap to this thing, okay, it takes 2 times as long to run because you have to evaluate f twice, but now it says that your code passes all the tests. So actually, this is like the #1 numerical differentiation bug I encounter in my office, at least once a year. Okay. I should note, by the way, that there's we can basically chain together expressions like this and get higher order derivatives. So for example, notice that if I did f of x plus h minus 2f of x plus f of x minus h, right? I can get that by just kind of rearranging these Taylor series some more. I don't think it's worth writing down. Then essentially we're going to end up isolating this guy now, right? This is all just different sort of reshapings of these 2 expressions on the board. And we'll see, of course, that then you end up with a first order accuracy because you're dividing by h squared. One kind of fun little interpretation here, which is nice, is that notice what's happening here, which is kind of cute. I can take this center difference expression. I could have derived that first one just by moving Taylor series around, or I could have derived it by accident by kind of numerically computing derivatives twice, right? Like this is sort of the numerical first derivative, and then divided by subtract and divide by h again, I get the numerical second derivative. These are just equal to one another. So this math actually justifies that that's actually an okay approximation. It also illustrates a very typical schematic in this area, which is that sort of the best approximation you tend to get is in the middle of the interval where you have data, right? Because all these symmetry arguments kind of work out. So notice like kind of a cute thing happened with this expression, which is if I have f of x minus h and f of x plus h, then the second order approximation I get is in between those samples, right? So then if I take the divided difference of these guys, I end up back at the, there's like a fence post problem, I end up back at x, which gives me my first order approximation. Kind of cute. Okay. Any questions about basic numerical differentiation? I think it's pretty straightforward, really. Now, for fun, I thought I would cover at least, this class. I would be remiss if I did not give you at least one numerical weird trick in every lecture. And it turns out even in numerical differentiation, we can do this. And in fact, this is illustrative of an entire class of algorithms. It's just that numerical differentiation is the easiest example, which are really, really beautiful. They actually originated, their history predates computers. They were used as sort of a proof technique in mathematics, and then somebody realized, like, oh, wait a second, this is also a really clever numerical technique. There's this whole class of algorithms called sequence acceleration, like that. Anybody ever encountered these? They're really fun algorithms. They're kind of neglected in the literature. There's probably some like boring machine learning graphics paper one could do by just revisiting these techniques. And in particular, the technique that we'll talk about right now is something called Richardson extrapolation, like that. Now, the idea of these techniques is really fun, I think. I think they're neat. The idea of these kinds of techniques is as follows. They say, let's say that I want to compute numerical derivatives, and moreover, for whatever reason, I live in a universe where I only know how to do first order accurate estimators. And basically the question I want to ask is, if I call my estimator more than one time, can I use that to construct an estimator which is higher order accurate? This is a really clever idea. So like in particular, remember why we talked about why central difference is so useful is it kind of widens the region where the h that we're using is kind of acceptable from a numerical perspective. You might ask a different question, which is, let's say that I compute 2 bad forward difference approximations, like an x and then 2x or something like that. Can I somehow like munge those together to get some estimate of how the error is changing as a function of h, and then use that to extrapolate what it should be at h equals 0? Really sneaky set of tricks. By the way, this happens all the time. It turns out the algorithm that we'll talk about is applicable to any iteration with this sort of bound on the error per step. which is fun. So this is one of these things. I'll talk about the specific case. I believe the textbook even goes through the general case of this algorithm. I forget. I should go back and look. Okay. So in particular, we are going to define a function d of h, just like before, to be f of x plus h minus f of x divided by h, like that. This is our favorite function of the day. And as we've already showed, this is f prime of x plus h. Wait a second. Oh, sorry, that was dumb. Plus 1/2 f double prime of x times h. Yeah, plus order h squared. Sorry. That just comes from the Taylor series that I erased. No, I didn't. They're up there. Okay. Everybody with me so far? All I've done is define a thing we've already worked with. Now here's what Richardson's extrapolation does. Oh, it's so cool. It's so clever. Okay. We're going to take alpha to be any number between 0 and 1. If that makes you uncomfortable, alpha equals 0.5 is actually perfectly fine. But it turns out that any alpha will work for this. And what we're going to find is you actually like a larger alpha often works better in practice. So here's the thing that we can do. We can evaluate d of alpha h like that, right? Now in particular, what's going to happen? Well, I don't think there's any reason to write the first expression, but we find that d of alpha h is still equal to f prime of x. But now, every time we have an h, we have an alpha h. So it's 1/2 f double prime of x times alpha h plus order h squared, at least assuming that alpha is a fixed constant here. It says alpha has no dependence on h. Everybody with me so far? I don't think I did anything too exciting. Okay. So I'm going to take this expression and that expression. I'm going to write them in a cute form, which is as follows. D of h, d of alpha h. I'm just going to stick them in a column vector. This is equal to a matrix times the vector f prime of x, f double prime of x. Like that, plus big O of h squared. Okay, so in particular, d of h is f prime plus 1/2 h f double prime, right? So it looks like f prime plus 1/2 h, like that, I think. Yes. And similarly here, we have f prime plus 1/2 alpha h f double prime. So this is that, then alpha h over 2. Cool? What do you think I'm going to do? Yeah.
Solve this like ignore the L of h squared.
That's exactly right. I'm going to multiply both sides by the inverse of this matrix. Such a cool idea. Like, this is just like one of those things that never would have occurred to me to even try. I don't know. Like this Richardson guy, he's onto something. So in particular, we have f prime of x, f double prime of x is equal to 1 h over 2, 1 alpha h over 2, inverse times d of h, d alpha h, like that, plus order h squared, like that. Make sense? Do you have a question or just a little h? Okay. Now here's the thing. Of course, I could stop here and solve this numerically, but that wouldn't be terribly exciting. This is a 2x2 matrix, so I can just write a formula for its inverse. I think many of you have encountered this before. So let's do that. This is such a cool trick. I don't know. I like this guy, this Richardson guy. Big fan. Okay. So in particular, this is one of those things that nobody ever remembers, which is the formula for the inverse of a 2x2 matrix. But the good news is that your instructor Googled it, and you have 1 over 1 minus alpha times minus alpha 1, 2 over h, minus 2 over h, like that. And then we have to carry everything over. So we have d of h, d alpha h, plus big O of h squared. like that. Fun fact. Okay. Now, right, so we could expand this expression. That's not terribly exciting. That's just matrix multiply. I think you guys know how to do that. Here's the more interesting thing. Notice this is an equality. So we can leave, sorry. So we can leave these first terms alone. We have, oh, it's not sticking. This is 1 over 1 minus alpha, dot, 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 d of h, d of alpha h, like that. Now here's the kind of interesting thing. This is going to happen when we talk about numerical ODE in our next lecture. What we're going to find is, like, if we solve a second order ODE, we can find cases where the different variables advance at different asymptotic rates. In particular, this is big O of h squared, but it's really big O of h squared, like a vector with two elements, both of which are big O of h squared. Does that make sense? So here's a kind of interesting thing. Notice the first row of this matrix has no h dependence, right? So really, it's like that. The second row has a 1 over h, so it's really like that. Does that make sense? Let's step back and think about that for a second. I see some furrowed eyebrows. It's okay. This is like a conceptual leap. Okay, so let's step back and think about what we did. It's also memorialized on the board here. D as an estimator, or by the way, D of alpha h, by the way, since alpha is a constant, is first order accurate, right? So like in order for D to work well, I need h to be like very small. Does that make sense? And alpha here is just some constant between 0 and 1. Like literally alpha equals 1/2. All the math will carry through here. It's perfectly fine. And notice, this is just some constant matrix, right? Like this is a thing that I could just pre-compute in terms of alpha and h very easily. In fact, let's say that I just isolate the first row of this matrix. Maybe we'll even do it for fun. We have f prime of x is equal to 1 over 1 minus alpha times minus alpha d of h plus d of alpha h plus order h squared, right? That's basically the theorem, the formula we just derived. This is true for any alpha. Do you see that? Do you see that a magical thing just happened? This is so cool. Think about it for a second. These are both first order accurate, right? So we expect these things to be bad approximation of the derivative for certain h. For that same h, if we combine those two expressions together, we actually get something that is higher order accurate. So this is the clever idea, oops, I'm missing a parenthesis, behind Richardson extrapolation, which is we take an estimator, which is bad, and we do it twice, and then we average it together in a very carefully derived fashion, and essentially what we can get is some kind of extrapolation that kills the first order term. This turns out to be a totally general strategy. If you go back through our math, what you'll be able to convince yourself is that really this works for any function of h that converges at a particular rate in terms of h. Like really this is just a Taylor series argument we wrote down. And this is just a general strategy for combining numerical derivatives in a way that makes them more and more accurate. By the way, you could repeat this argument, take two second order accurate things and make a fourth order accurate thing or something like that. Really sneaky. Now, why does this matter from a numerical perspective? Well, it's exactly the same as using central difference in the sense that now, if I choose h to be much larger, I can still get a smaller amount of error in our approximation of f prime, thus avoiding some of the numerical issues we had before. Does that make sense? Yeah, Jonah.
So in practice then, why do we not just go up to like an 8th order thing?
Why don't we just keep doing this? You absolutely could. There's two things that go wrong. For one, by the way, at some point, like it's just not worth it. Like, I think there are very few functions that are so wiggly at a local level that that's necessary. Although I kind of suspect, I was thinking about that in today's lecture. One thing that's well known about neural network functions is that at a very microscopic level, they tend to be quite oscillatory, even though like at a broader level, they're smooth. And so I kind of wonder if some of these tricks need to be revisited. But okay, it's pretty rare to encounter a situation where you really need such a tiny h for your approximation that this is required more than once. The other thing that can go wrong is notice that we are taking like weighted averages, including some minuses here. So these rules, just like our quadrature rules, can become unstable if we chain them together. Now, there's a different question, which is what alpha should I use? Right, so notice what this thing is doing. It's saying this is distinct from central differences. Notice that like if alpha is positive, it only ever looks to the right, this particular expression, right? So like what did we just show? Although I guess actually there's nothing stopping alpha from being negative in the proof. I have to think about that. We showed that like, okay, we have h over here, we got 0 there, we've got like alpha h somewhere in between, right? Like alpha equals 0.5 somehow feels right from symmetry. Notice that this, again, this is doing an interesting thing, which is this taking this divided difference and that divided difference, and then using them to approximate the derivative there. This is distinct from central differences. However, notice that there's kind of an interesting push-pull here. If alpha goes smaller, then we expect this term to be more accurate. That feels somehow useful. Notice that if alpha goes to 0, then basically you just don't weight that first term at all, which makes sense, right? Because you should rely on the more useful derivative. However, as alpha goes to 0, we encounter numerical problems. So I think actually a very typical thing to do is to choose actually fairly large alpha, right? Because those are the divided differences that are less likely to run into catastrophic cancellation. And as long as alpha is any number between 0 and 1, like 0.9, this formula is still okay. So anyway, it's a really clever trick. Essentially what you're kind of doing is extrapolating the error to h equals 0 in a way that works with a higher order accuracy. Is that a fun trick? I think like you guys are likely to have seen these Taylor series. I think you're less likely to have seen Richardson extrapolation. So in any event, by the way, I should have put this plot earlier. I actually did this experiment in MATLAB because I'm a bad person. And indeed, you can see that like this is a very typical way that these plots look, where essentially I'm trying to differentiate some function. I forget which one that is. I think this is cosine. And the numerical error as h goes to 0 starts to blow up. And then eventually it's smooth, but it's also positive, which is bad. Yeah. Any questions so far? Yeah, I think this is pretty straightforward stuff. In our last 15 minutes, I mean, I don't think it's worth covering in more detail because all of you guys are probably going to take some other class that covers this stuff in much more detail. I do think any numerical methods lecture on differentiation has to at least mention that there's an entirely other class of algorithms out there, which is, I think, the dominant class at the moment. That's called automatic differentiation, or autodiff. Or as it's better known, at least in one particular example, we call this backprop. I think it's kind of interesting if you dig through the history of this algorithm because it's somehow very natural. It was discovered and rediscovered a bunch of times as people fight over who owns it and who should get the Turing Award and all that good stuff. I'm not going to dive into that nastiness. Academia is a small and petty place. However, this is essentially just like basically glorified application of the chain rule that says that for a lot of functions that we care about, in fact, most of them in a lot of computational applications, we don't need this divided difference stuff at all. We just need a better way to do the chain rule. Right? Notice that this depends on your application. Like there are some universes where like I don't have access to a function. I like went out in the world and I collected a function on a grid of points and I just don't have it anywhere else. Like I put a satellite out there and I want to know like the change in elevation. In that case, the kinds of approximations we've done in today's lecture make a lot of sense. In other cases, like I have a piece of code for evaluating f of x, so I can put in any x that I want. Then it's a little bit less clear that these approximations are really worthwhile relative to just working out the derivative formula, in which case you wouldn't have any errors of function h because there's no h. By the way, these things get confused a little bit in modern machine learning literature. Like sometimes, for example, in computer vision, you're learning these objects called neural fields, which are functions of like 3 to 5 variables. And actually, the approximations here can be less expensive than doing a full backprop. But that's a thing for another day. But essentially, there's this whole other class of methods out there. The textbook also has discussion of these things called automatic differentiation or autodiff, that are kind of like saying rather than doing numerical tricks, I'm going to do like compiler tricks to get derivatives of functions in some sense. In other words, what we're going to do is we're going to make a piece of software that makes it a little bit transparent to the programmer that, in fact, when they implement an expression, not only am I going to get that expression, I'm also going to get the derivative of that expression with all of its variables. And here's the way to kind of think about it from like 100 miles away, notice that like it felt hard when you took calculus the first time, but like there's this asymmetry in calculus class where like integration is somehow this weird bag of tricks, and most functions don't have closed form integrals. We don't know what to do. But differentiation is very systematic. There's like a few rules that you have to learn, and then you just go through them 1,000 times. And it turns out they are so systematic that you really can just write them in code and then just implement them as part of the mathematical operations that your software knows how to do. Okay? And that's what these automatic differentiation tools are doing. There's sort of two different versions. In a more comprehensive lecture, for instance, if you take my 6C01 class in the spring, we'll do a whole lecture and a half on this stuff. There's sort of two different modes in modern software, including what? PyTorch, TensorFlow. I don't think people use Cafe anymore. JAX, some of these other ones. They all implement both of these things. The easier to understand one is the less popular one called forward mode. Which does the following thing. Let's say that I have some function f of t. Now, typically, I write a piece of code for evaluating f of t. Like, so for instance, I don't know, f of t is cosine of maybe 1 plus t squared, something like that. Right, so what do? I have a piece of, like a t that goes into my code. I multiply it, I add 1, I do cosine, and I do this one line of code at a time. Then essentially, the big idea of forward mode automatic differentiation is as follows. I am going to make a new data type, like a new version of a number. So far, we've talked about like floating point and double precision. In the simplest case, here t is just one variable, so it's particularly easy. What I'm going to do is have a pair of things. I'm going to have like some value v, and then a second thing, which is like dv dt. And behind the scenes, what's going to happen is every time I type a piece of code, it's going to update both of these objects. Okay? So in particular, let's think about the following. So as input, now I have t, and what is dt dt? 1. Thank you, Alicia. Somebody's awake. Okay. So now I compute, so essentially what we're going to do in forward mode automatic differentiation is rewrite all of our operations to update both the value and its derivative at the same time. So for example, let's say that I had u and u prime. I guess prime and d over dt are the same. And then v prime like that. So in other words, I just have like a new plus sign operator. Well, we know that derivatives are linear, so we have u plus v as the value, and then u prime plus v prime behind the scenes. So the programmer just uses a plus sign. There's no pair here. They just use one of these autodiff types, and this happens behind the scenes, right? Now, for example, let's say that I take a product, so I do u prime, and I multiply that by v prime. Now, behind the scenes, what's going to happen in your multiplication? Well, the first element of the pair is still just the value, so that's just uv. The second one is going to be what? It's going to be like the chain rule, right? So it'll be like uv prime plus v u prime, right? So basically what happens in forward mode automatic differentiation is just like in your code, rather than using a double precision type, you use a forward mode whatever type. And now you type exactly the same expressions you had before, but behind the scenes, every time you have a new expression, it also has a rule for computing its derivative. Or so, for example, if I had like, maybe to do one more, if I had cosine of u prime, I would get cosine of u. What's the cosine? Minus sine of u, that's right. Is this correct?
U prime
Times u prime, right? Because remember that u is itself a function of t, so have to be a little careful of the chain rule. Right, so I just implement, that was a u, by the way, sorry. A bunch of rules of this form, one after the next. This is like in C++, so you call this operator overloading. And then it is transparent to the programmer that behind the scenes, every time they type an expression, it's also computing the derivative of the expression with respect to the inputs to your code. Yeah, Jonah?
Does this require you to have a base derivative, u prime and v prime of these things?
Yes, so this requires in step 1 to define all of the variables with respect, respect upon which you are going to differentiate. Yeah, and that is actually the main drawback of the forward mode automatic differentiation. So typically in machine learning, you're not a function of just a single t, you are a function of all of the parameters of your machine learning model. So think about like all of the weights of your neural network. And moreover, you are doing tons and tons of intermediate calculations. So then the size of this calculation scale is like the product of those two things, which is typically too big. So this is why you don't encounter this particular algorithm in machine learning for high dimensional stuff, at least in version 1.0. So that leads us, thank you, Jonah, to a different thing, which typically is covered in like 3 lectures in a machine learning class. We have 5 minutes, but you guys are smart, so I'm not worried about it. Called backward mode automatic differentiation, which does a very different thing. Notice, by the way, that in forward mode autodiff, you kind of like, you can halt your code at any point and you'll have the derivative and the value. In backward mode, you do a very different thing, which is build up the expression that you're trying to compute, and you say, okay, I'm done. And now it's saved the whole chain of calculations that you did to get that expression, and it does a different calculation to get the derivative. Okay? And this all happens at the end of the thing. So, okay, so this is called backward mode. By the way, I'm like not very happy with the discussion of this in this textbook. I'm also drafting a textbook for 6C01. If you email me, it has a lengthy chapter on autodiff in there, which is, I think, much more approachable. By the way, this algorithm is kind of called back propagation. Again, there's a lot of debate over the exact origin and definition of this phrase because it was originally derived specifically for neural networks. Or originally by the person that called it backprop did it for neural networks. Okay, and so here's the basic idea. Let's say that I have a piece of code y equals f of g of t. So for example, like cosine of 1 plus t squared, right? Then let's think about, let's build up this object called the computational graph, which is kind of like the path from the input to the output, okay? So here's a very typical thing to do. I have t, which goes into my code. I evaluate that, and just to agree with my notation, I get maybe z is equal to g of t, like that. And that thing it leads me to my output, which is y, which is equal to f of z. And notice that I've basically taken my calculation and just broken into 2 lines of code. Does that make sense? Okay. So here is what backward mode does. It says, okay, and now I say, aha, this is the output. This is what I want. So I want the derivative of y with respect to t, and now, but only y. I don't really care about the derivative of z with respect to t. That's the difference. Notice that along the way, in forward mode, you also compute that other thing. Okay? So in backward mode, originally you just do your calculation as it was. Nothing changes. Now you freeze, and you say, okay, now I want the derivative of this thing with respect to t. Notice that there's already a big advantage, which is typically in machine learning, this whole thing over here is like your loss function, like the thing you're actually trying to minimize. This is typically a scalar, right? Whereas up here, you had all these intermediate values, which you might have differentiated with respect to t, which could be quite big, right? So this is typically in R1, okay? So here's the idea. I'm going to compute d over d, or sorry, I'm going to compute dy d everything else, right? In forward mode, we did d everything dt. Here, we're going to do dy dy, and then dy dz, and then dy dt. Do you guys see how this is different? One of them is like the numerator, and the other is the denominator. Okay, so first of all, what is dy dy? Well, it's just equal to 1. Okay? That much we can do. Now here's the kind of clever idea. Now what we're going to do is we're going to have dy dz. Notice that this calculation needs no knowledge of what happened before z in the computational chain. This is different than forward mode. And what is dy dz? Well, it's equal to, in some sense, dy dy times dy dz, which is basically, you know, whatever, dy dy, which is this value in this other part of the chain. Dy dz is just f prime of z. So the basic idea here is that I can calculate the derivative of each of these of y with respect to each of the intermediate variables by combining what information. Well, notice that there's a z here, so that needs to go there, and information from the previous link in the chain. Similarly, so now I have the derivative of z with respect, or y with respect to z. I'm going to keep messing this up, I'm sorry. Now I want, I want dy dt. Well, this is equal to d y dz times dz dt. Right? Well, here's the good news. We have dy dz, so our backprop system just stores it, right? And now, what is dz dt? Well, it's just g prime of t. So once again, notice the information that goes in is like that, right? So do you guys see how forward mode and backward mode automatic differentiation are different? One of them just goes forward through the pass, and at every step it computes the derivative with respect to t of our current variable. In backward mode, you do the entire forward pass, and then you go backward through your calculation. And in each case, rather than computing d over dt or something, you're computing d loss d something, right? That's the difference between these two things. Now, why is backward mode autodiff so popular in machine learning? Well, essentially, in machine learning, the thing we typically are wanting to differentiate is just a single scalar value. It's the number we're trying to minimize. And so the size of each of these intermediate variables is linear, whereas in forward mode, you can end up very easily with like quadratic or even at larger scale. Does that make sense? That's really it. I mean, I think especially in a graduate course like this, it's so easy to get lost in a machine learning course when they talk about backpropagation and they draw all these like stupid diagrams with the like circles and the, you know, like the whatever. Like in case you guys haven't figured it out by now, this is just a matrix multiply. That's it. I don't know why people are so averse to matrix multiplication in that community, but the reality is that like if you think of backward mode, autodiff, and backprop as just systematic application of the chain rule, then it's pretty easy to see what's going on. By the way, in like software like PyTorch, all of this happens. You evaluate your loss value, and then there's this magical function called loss.backward. Right? And essentially what happens in backward is as you built up your expression, it just keeps all of these intermediate things around in some sense, and then just does this pass in the reverse direction. That's it. That makes sense? So again, what are the advantages and disadvantages? The advantage is that typically this object is low dimensional, so the intermediate variables are relatively small. The disadvantage is you got to remember your whole calculation. Yeah, Jonah, we're already over time, but.
Just still in this case, we still need to have each of the f prime, g prime, etc.
That's right. Yeah, no, to be absolutely clear, this is not some magical reshuffling where your derivative has fewer arithmetic operations, exactly the same number. What's different is the size of the intermediate variables. It's like a storage thing, largely. Yeah. All right, guys. With that, have a delightful rest of your Monday. I believe we have 2 lectures in this course. We're getting very close. Next time, we'll talk about differential equations.